Hello everyone, my name is Ali Shokri and I'm a PhD student of computer science at Rochester Institute of Technology, New York, United States. And today I will be presenting my research, which is around using program synthesis approach for synthesizing architectural tactics and adding them to a current code base. And if you're not familiar with some of these terms, don't worry, I'll provide enough background before jumping into the method. So software architectural tactics are among design decisions that are responsible for some important quality attributes of a system, including security, availability, and performance. In the subsequent implementation phase of software construction, in case that there will be deviations or drifts from the envisioned design, we might end up in a software with severe bugs, flaws, or vulnerabilities. These tactics are mostly implemented using API of third-party libraries or frameworks. And studies show that in 95% of the time, API misuses result in software crashes and those mentioned problems. Although there are some tools developed to analyze the program, identify API misuses, and notify the programmer, they are not really usable for novice programmers as they don't have enough knowledge around architecture, structure of the code, API, and so on to properly leverage those notifications. So one solution for supporting these programmers would be automatically implementing the tactic and adding them to their code. Interestingly, there exists a branch of computer science that its main focus is on automatically constructing or synthesizing programs. These approaches take the specification or characteristics of the to-be synthesized code from the user and try to create a program that satisfies those specifications. Then in an iteration, it verifies whether the created program aligns with the user expectation or not. If it is, then it outputs the program. Otherwise, there might be some more iterations. There is one sub-branch of program synthesis, which is called component-based program synthesis, that aims to create programs by wiring up components, in our case, APIs, that are specified by the user. So, as this example also shows, the output of this approach is a program that is only built from APIs. So, it's been over a decade that component-based program synthesis has been introduced. Some of these approaches consider elementary operations in a program language like addition, subtraction, and so on as components and create programs out of those components. There are also more advanced works that particularly create programs from a given list of API. But starting from 2-3 years ago, some approaches incorporate knowledge about API usage and misuse in their synthesis task, and studies show that the synthesizer's performance can tremendously improve. However, there are two issues with all these works when it comes to architectural tactic implementation tasks. The first one is these works require the programmers to provide the specification of the to-be synthesized code, and in case of novice programmers, due to their lack of knowledge of architectural tactic, code structure, and API, it's not possible. The other one is these synthesizers create a block of code and leave the task of breaking it down to smaller pieces and adding each piece to its corresponding location in the code to programmers. And again, this is a challenging and error-prone task for novice programmers. So in my research, I'm aiming to develop an approach that automatically infers the specification of the tactic and synthesizes it and adds it to the code. This specific research has several aspects of uniqueness. For example, despite the other approaches that require the programmer to provide the specification, it tries to automatically capture the specification from the under development program. Also, instead of asking the programmers to split up the synthesized code to smaller pieces and add them to the corresponding location, this approach is supposed to synthesize discrete pieces and automatically add each part to the location. So this is an example of how the approach should work. Given a compilable program which does not implement the tactic, which is in the left side of the screen, and some knowledge about APIs, then the approach should be able to synthesize tactic, add it to the code, and output the program which correctly implements the tactic. So the approach that I'm introducing consists of 5 steps. As I mentioned before, the approach takes in an API usage knowledge as an input. So in my prior work, I was able to develop an approach which is called RCode that learns correct ways of using APIs for implementing architectural tactics from 2 sources, the source code of the framework and a repository of code that includes programs that incorporate API of that framework. We also were able to create a tool on top of this approach that is able to analyze programs and identify API misuses, possible API misuses in the program. If you're interested in this work, I would encourage you to take a look at the papers that we published at ICSA 2021 and ICPC 2021. So we use the framework API specification model that is learned by RCode, which we call it FSpec, and we use it throughout our synthesis approach. So in the first step, we go through the framework API specification model that was generated by RCode and create hierarchical clusters of APIs such that all APIs in a cluster contribute to performing a unit of task. We create clusters based on similarities of method names in which APIs in the FSpec model were obtained from. Then within a cluster, we find the method name of APIs that has the least square distance to other method names, and we select that specific name as the label of that cluster or the annotation of the cluster. At the end of this step, we will have an annotated FSpec. So for each annotation in the FSpec, we try to find candidate locations in the code such that APIs in that cluster can be used to synthesize the code snippet and then be added to that specific location. We use different metrics to quantify the worthiness of mapping and annotation from FSpec to a location in the code and assign a score to it. So for instance, based on the Levenshtein distance metrics between the method name of where the location is placed in and the annotation name of the cluster, we compute a score. Moreover, since in each cluster there are some APIs and each API might need input arguments, we analyze the program and see how many variables with the same types as the API argument are initialized and visible at those specific locations. This will result in another score for mapping an annotation to a location. Then we use these metrics to generate a single score, which the score is between 0 and 1 for each mapping. At the end, we create a rank list of annotation code location mappings and basically annotate locations in the code with FSpec annotations. So far, we were able to find out which annotation should be added to what part of the code. In this step, we move towards actually generating the code. So based on APIs in each cluster of FSpec and their data and control dependencies, which are in the form of a directed graph, we translate that graph to a piece of code in the form of static single assignment or SSA. There might be APIs in the code snippet that need input arguments, and some of the arguments will be provided from the output of other APIs. However, there might be still some unfilled arguments remain. So in such cases, we analyze the program and find initialized and available variables in that scope that have the same type as the input argument. In case that there are more than one available variable for an argument, since we cannot make sure which variable should be used, we put a question mark or a hole instead of that argument. We basically are creating the structure of the code in this phase with some holes remain in it. The goal of step 4 is to resolve the remained holes in the code snippet. So in this step, we translate the original problem of finding a proper variable for each hole to an SMT problem. It will be in form of CNF for those of you who are familiar with logic in general. And each part, the DNF part, would present all the possible variables for each hole. Then we solve the problem using the popular off-the-shelf SMT solver Z3 and find the minimum variables that can satisfy the whole sentence. Finally, we translate back the solved problem to the space of our original problem and assign the found variables to their corresponding holes. So at the last step, we verify the synthesized code to make sure that it's syntactically and semantically is correct. For checking the syntax of the generated code, we parse the code using Eclipse JDT. And for the semantic correctness of the synthesized tactic, we analyze the code using RCode tool and see if there are any API misuses in the code. And in case that there are no syntax or semantic errors, we mark the synthesized code as a verified one. So we have been able to create a data set which is for the first time that someone created this type of data set that includes software architectural synthesis tasks. And the test cases are basically the correct programs that implement the tactics, and we remove the tactic implementation part of the test cases. And the test labels include the original locations that tactics were found. And in addition to that, the potential correct locations that if you add the tactic to, again, the program will be semantically correct. So we gave these test cases to our approach and observed the performance of the approach in different scenarios. And we wanted to see that if it can correctly synthesize the code or not. We particularly evaluated the approach in 2 different levels. So first, we focus on each step to see how the approach worked in each step, and then we evaluated the entire approach. So in the case of stepwise evaluation, as you can see, for the code annotation, our scoring system shows a very high accuracy in finding candidate locations. And the sketch generation and sketch resolving also, they show the very good performance on the created test cases. We also examined the overall performance of the approach based on the semantic correctness of the synthesized code. So we did that through a manual inspection as well as an automated tool-based approach. In both the cases, we received a very high accuracy in terms of the semantic correctness of the approach, of course, with respect to API usages. But for the tool-based approach, we use the RCode plugin tool to identify possible API misuses. And we actually believe that this would not be fair to use RCode for the evaluation, since we used it for the verification step in the approach. So we're currently looking to find another tool-based approach for the purpose of semantic correctness evaluation, basically the automatic evaluation. Although this dataset is introduced for the first time, but it has its own limitations. So for instance, we are using APIs from one framework, Jazz framework, which is a popular Java framework. And the number of test cases are limited. There are 10 test cases. So we are looking to adding more test cases and frameworks to this data set. Also, the approach is able to generate loop-free tactics, meaning that there will be no while loops, for loops, and so on in the synthesized tactic. We are working to add this feature in the next versions of the approach. And moreover, we rely on naming similarities in our approach to find the correct locations in the code. But in case of, for example, obfuscated codes that the method names are changed, that might be problematic. So we want to add more semantic-based approaches to find the correct locations, including data flow analysis and control flow analysis for finding the correct locations, as I mentioned. So in this talk, I provided a brief introduction to our approach in the paper, although this is an abstract, external abstract, but you might find more details. Thank you, everyone. Have a good day.